One of the interactions that we see between electric current and a magnetic field is that there's a force that is created due to the interaction. Now, if you notice in this drawing, we have a current flowing from front to back through this wire. Magnetic field is going from left to right, and there is a force in the down direction. And if we were to change the direction of the current, then, and the magnetic field stays the same, then the force direction is going to be in the opposite direction. And this appears to follow another right-hand rule. If we take and put our fingers in the direction of the current, and then bend our fingers in the direction of the magnetic field, then our thumb will point in the direction of the force. This is the right-hand rule. Now, anytime we look at two vectors and the resulting vector is in a third dimension, this should make us think of the cross product. And this is a true example of a cross product. So the force vector is equal to the current, which is a scalar, times the L vector, which is the amount of length that the current is in the magnetic field, cross product of the magnetic field strength. Now the cross product can be simplified, and just to give an example over here, if I have C vector is equal to A vector cross B vector, then my magnitude of C is going to equal magnitude of the A vector times magnitude of the B vector times sine of the angle that the two make with each other. So in this case, I can have that the force magnitude is equal to the current times the length that the current is in the magnetic field times the magnetic field strength sine of the angle between them. And we just notice that this is the maximum. F max is equal to ILB when theta is equal to 90 degrees, because that will make the sine a 1. Now we can also look at if things are changing. We can look at this cross product as a differential. So we can have differential F, the differential force, is equal to, remember that I is a current, we can have L vector cross dB, meaning that the magnetic field changes through the length, or we can have the differential force is equal to I differential length, but the magnetic field remains constant. So now we have a situation where we are going to be integrating along a line. And you may not have done this before, so before we can talk about how to do problems, we need to talk about how do we come up with this differential length if we're going to be able to solve a problem. So in the next video we'll talk about coming up with this differential length based on different forms of a function.